Hello, and this is going to be a rather interesting video that looks at a slightly different aspect of the flat earth that I don't think that I've seen too many people talk about. I had a recent encounter with somebody on Twitter that tried to imply the reason why we see the sun go down on the horizon on a flat earth is because of perspective. And I was already working on this in a slightly different way, but I think that it really tied together with that discussion. Before I continue with that, I just want to show a few things that I've done. I've already provided this link on Twitter, and it's a spreadsheet that I created from a data file that I used for PovRay. The essence of this data was already shown in not my previous video, but the one before it. And the data set is fairly simple. I'm just going to walk you through a couple of examples very quickly. If I pick this one, for example, 80 degrees north, 80 degrees east, put that in SunCalc. In this case, it's UTC plus 7, or it has to be 9:01 p.m. So the altitude, according to SunCalc, is 19.79, and the azimuth is 293.46. There is a small tolerance in the equations that I'm using. It's not exact, but you can see that it's almost identical. Let's try a different one. Let's pick this one, 60 degrees north, 90 degrees west. Here I have to subtract 2 hours. Oops, that was -5, not -6. So I had to go to 9:01, and here I have 34.93 and 103.80. So that's how I confirmed the altitude and azimuth readings for all of my latitudes and longitudes. And then from there, I got my computer to generate where the observer, where the sun should be, and where the arrows should be in 3D space if it was a globe. And then I did something similar if the Earth was supposed to be flat. And this entire spreadsheet is to illustrate the math that I use to calculate where the sun should be on a flat earth. This is how I did it in the spreadsheet. These are the numbers that the application generated, and then I just subtract the one from the other. And as you can see, except for a few small rounding errors, the values are virtually identical. I'm going to leave the link to this spreadsheet in the description below if you really want to look at it. Keep in mind that if we take away how some flat earthers believe that our eyes somehow optically make the sun appear to be lower than it really is, if we assume that light is supposed to travel in a relatively straight line, unless of course it's been demonstrated to change direction by going through different medium densities and by gravity, then we should assume that the rays of light going over a flat earth should be straight. If we ignore what flat earthers say about the eyes doing optical manipulation and optical whatever, then where we perceive the sun to be by looking at altitude and azimuth readings and using simple trigonometry to calculate where the sun should be from the observer in three-dimensional space, the difference between these two should be the same if it's vertically or horizontally. We can see that the altitude observed goes all the way down to the ground and even below horizontal. If the angular difference between where it should be on a flat earth and where flat earthers think that it is because of the way our eyes work, that angular difference vertically should be the same as the horizontal angle. Given distances, given everything, the sun should never appear below 8 or 9 degrees above horizontal, and yet we can see that it goes all the way down to the ground. So if the sun is really up here and it appears down over here, a total of 8 or 10 or 12 or 15 degrees depending on where you are on the earth. Let's say it's 15 degrees. Then the azimuth reading should not be any greater than 15 degrees this way either. Otherwise, there's a completely different factor going on. That's the point of this video, and that is going to be the point of these animations that I'm creating. I've created a whole bunch of PovRay scene files. You can look at the raw numbers all you want, or you can run it through PovRay to see exactly how it looks. Here is the date, including the time zone. This is the geo-coordinate where the sun should be directly overhead. So in this case, I'm going to put this overhead geo-coordinate into SunCalc. You can see the altitude is directly overhead. So this is going to be the geo-coordinate where the sun is directly overhead. That's going to be the date and time. That's the Unix time. This is where the sun should be in 3D space. I've added a few extra values in, and that will be used in some of the modes. This set is for the globe. These values are for the flat, and these are globe and flat. So I have an array of 25 elements. So this is a two-dimensional array, 631 by 25. These are the offsets and what they are. So if I want the three-dimensional space for the flat Earth, it's going to be 16th, 17th, and 18th offset. Keep in mind this is 0 base, not 1. And this script is going to be made available. It's also going to be linked in the description below. This script has 6 different view modes that you can choose from. And the first is going to be looking at a fixed point above the Earth. In this case, you're looking at 90 degrees west along the equator. Second mode is where you're looking at the Earth from a point between the sun and the Earth. The third is going to be where you can choose from one of these pre-generated coordinates that go around the Earth, kind of in a flyby. The next 3 modes are for the flat Earth. This one is looking down at the North Pole from 90 degrees west. So you're kind of looking down at the flat Earth kind of at an angle like this. The next one after that is going to be looking straight down at the sun. You're going to be following the sun as it goes around the Earth. You'll see that in a minute as well. And the last mode that I don't have an animation for is where you're looking at the sun from one of these flat Earth positions, which would be these coordinates here. So you would have to go and find the offset that you're interested in based on these coordinates. So you'd have to go 67 in this case and mode 5. And when you render it, you'll be looking at the sun from the ground. Like my last script, this allows you to change the files externally through an external script, for example, and you can override these values. I'm going to remove these before I make them available, but I'm just doing this so that you can see it and I don't have to change this file externally. Then it loads the scene file in question. These are macros to place objects. This macro will check to see if it should draw that object based on the altitude. This will calculate the location for the camera and where to look at based on the mode. Then I set the camera up, and if it's the globe Earth, then I will place the light source and draw the sun, draw the Earth, draw the arrows that point from the Earth back to the sun. And if it's a flat Earth, I will place the flat Earth sun, draw a box with azimuthal equidistant projection map. Finally, draw the arrows for each of the geo-coordinates. And I've added this, I'll leave in for now. You can play with it if you want. It allows you to selectively enable or disable the arrows for certain latitudes and or longitudes. You can figure out how to do that this is for latitudes, but you can figure out how to do that for longitudes. It's going to be changing this value here. Finally, I'm going to show the animations shortly, but this is the result of all of this. I calculate the direction that the sun should be, and by looking straight down, I'm primarily focused on the azimuth, not the altitude of the sun. And you can see that the azimuth is pointing very far off from where it should be. First, I'm going to insert this animation. As you can see, all of the arrows point in the same direction. Next, I'm going to show where the sun appears to be in the sky for the flat Earth, if the sun is supposed to be directly overhead. As you can see, it is a really serious looking mess with the sun pointing in all different directions. Then I decided to tame it down a little bit and only focus on a few of them. You can see it really doesn't help much. Finally, I focused on a few choice latitudes, looking straight down where the sun should be directly overhead. And as you can see, the azimuth readings are really all over the place. If you are interested in these, please see the description below. All of the links and various resources that I have should hopefully be in the description. That's it for now. Please feed the YouTube algorithm troll, and I will see you again in another video, hopefully soon enough. So bye for now.